everybody joining, both in person and online. My name is Owen King. I'm Director of the Galway Sound Lab, which is a new research group here at the University of Galway. So to begin, we're very excited to present Jeff Parnell today to give a talk on wind turbine noise. But to begin, I thought I'd give you a quick intro to the Galway Sound Lab and some of the work we're doing. So the Galway Sound Lab is the Centre for Research in Acoustics, Noise and Vibration at the University of Galway. That's our beautiful skyline in Galway. We have a variety of projects ongoing, some of which are very relevant to today's talk. The first one, Assure, is an SEAI funded project. It's a 4-year project looking at noise propagation over water. So with a particular emphasis on offshore wind turbines, the soundscape, the impact offshore wind turbines will have on coastal soundscapes in Ireland. The WindSense project is an IRC funded project. It's now complete. That was in partnership with the Department of Psychology. Dennis O'Hora, who's a lecturer in psychology here, was a co-PI on that. In that project, we did listening tests to assess impact, psychoacoustic impact of annoyance from wind turbines, and we also developed something we've called a noise annoyance map. So instead of developing just noise map for wind turbines, we're actually developing annoyance maps for wind turbines. The third project is Shellwise, which is a 4-year project. It'll be kicking off in September. So while Assure was looking at sound propagation over water, Shellwise is looking at sound propagation underwater, and in particular, its effects, or the effects of noise on marine life. So that's in partnership with a zoologist, Christopher Coates. So that's kicking off in September. Separate to wind turbine noise, we've got projects related to room acoustics. So Room Phonic is looking at indoor soundscapes and their effects on workplace noise productivity. The Standardise project is a project funded through Construct Innovate from the Department of Housing. That's a big project which involves partners from UCD and the University of Galway. From an acoustics perspective, we're looking at modern methods of construction and the impact of those modern methods of construction have on acoustics. And then we have 2 other projects related to environmental noise. The first is ANITA, which is funded by Transport Infrastructure Ireland. That's looking at road traffic noise, and we're developing new guidelines for road traffic noise in Ireland for new roads. And then Noise 2050 is a brand new project. It'll kick off in September. It's funded by the EPA, and it's a partnership between Trinity College, UCD and the University of Galway, where we're imagining what Ireland's soundscape will be in 2050, what will be the noise problems in 2050, and what do we have to do to address those problems now. So that's a quick overview of the Galway Sound Lab. Here is our team. There's myself, Dennis O'Hora, who's in psychology, Mohammed Gulzari is in UCD, Manish is a postdoc. I've got Eugene, Sean and Patricia, our PhD students, and Dara Mullins is our technical officer. But we have new members coming on board, Christopher Coates, Owen Murphy, and 2 new PhD students. So we're a growing research area looking at all aspects of acoustics and noise control in Ireland. That's it from the Galway Sound Lab. So now I'm pleased to hand over to our special guest speaker, Jeffrey Parnell, from the University of Technology, Sydney. Myself and Jeff go way back 20 or so years. When I was just finished my PhD, Jeff helped me with a lot of work on road traffic noise, wind turbine noise, noise from mining activities. He helped me with my book. So we go way, way back. So Jeff is currently an adjunct professor in University of Technology, Sydney. He's worked with the EPA in Australia, Department of Planning in New South Wales, and he's a past president of the Acoustical Society of Australia. I am delighted to hand you over to Jeff.
Thank you very much, Owen, and thank you for Engineers Ireland for the invite to present to you. Thanks also to my other connection from the consulting side of things, Dermot Keamy, who was also reciprocated by presenting to us in Australia, to our society there. Guys, what I'm going to talk to you about tonight is a couple of things really here. So we'll go through a little bit of turbine 101 noise and predictions, but really I know that most of you who work in this area know what's happening in the contemporary design and generation of noise. So we won't go into that too much. What I will talk to you about is the Australian legislation. I think that's something that's going to be quite a lot different to what you have over here. I'll talk about how that affects wind farm regulations and how we developed our guidance in Australia. It's been quite a different process than normally happens in other countries such as England and that you guys might end up copying a lot of. I'll talk about the new documents that came out late last year that I had some involvement still in, which was the New South Wales Wind Energy Guideline. And then time permitting, I'll talk about another couple of things that are ancillary in the renewable area, and that's solar energy. I'm not so sure that's going to be a topic given by the amount of sun that I've seen in the last couple of weeks that I've been here, so we might end up just skipping that. But certainly battery energy storage systems will be something of interest to you here in Ireland. And the other thing that I'll talk about, where we look to you guys for guidance, has been the work on transmission lines, which are actually becoming quite an issue for us. So without further ado, I'll move on. Okay, so just quickly on some statistical metrics. The things I'll be talking about today here are just using the LAQ 10-minute and the background noise level, also an L90. I think most of you that are familiar with this, some of the things we'll talk about today is going to be L-maxes, L10s, LEQs, and L90s. I think you probably mostly would know some of that, and mostly with wind farms, it's about measuring an LEQ level and then excluding what the background is, which is often quite difficult to do. So with turbine designs, sorry, Owen, is that top level top bar?
No, it's clear online.
Oh, okay, so long as it's clear online. Okay, great. So what we've been finding here in Australia is since we started looking at wind turbines and they started being prolific in the country, they went from well under a megawatt. We've got onshore ones that are now pushing over 6 megawatt turbines. So the thing that we are seeing is though that there isn't really a clear relationship between noise emissions and the size or actually even the hub heights of these things. So there's a lot of things that come into play there. There's been a lot of development, and I'm sure those of you in Ireland and Europe would also be looking at the same things. It's been the blade design, rotational speed. We're finding all those issues with trailing edge noise that we are putting serrations on the backs of blades. It's fairly universal that they'll be stuck on the backs of blades now to reduce some of that trailing edge noise that becomes a little bit problematic, and that also helps a little bit, I think, with the amplitude modulation and so forth. But as you can see from a couple of the graphs there, there's no real reasons, rhyme or reason there with some of the sound power levels that we get from different rotor diameters and different heights. They seem to be a bit all over the place. And that was mainly looking at some data from Vestas that there is a lot of fairly good information on. Sound power curves, nothing really unusual here. If you don't know it, wind turbines start to kick in at about 3 meters per second at hub height will be about the wind that you need to start your turbine turning, and you'll reach rated power at somewhere around about 10 to 12 meters per second at hub height. And your sound power levels will keep going up, and they'll rise up there till you're around about the 95% of rated power, and then we kind of get a plateauing of that effect, and then they're just constant after that. Spectrally, we have seen quite a bit of difference between some of the turbines. And if you're just looking in dBA, it's going to give you some different results. So So one of the things that we are looking at, and it's a thing that needs to be looked at by the consultants that end up going and measuring these, is what the spectral information is. There's an example of three turbines there that ultimately you wouldn't really pick which is the most problematic one there. But if you start looking in dBA and then you start going out at different distances, where you start getting differential attenuation of the higher frequencies, you do start to see those lower frequencies come in and start to dominate. I will be talking in this presentation about distances that are setback distances that are quite different to what you have here in Ireland. So be mindful that we do have most of our receivers out at greater than 1,500 metres, which is, you know, like a 3 times factor on what you often have here in Ireland. Moving on, talk a little bit about propagation. Wind enhancement, we're obviously going to get that in turbines because otherwise they won't be working. So we've got that downwind propagation that you'll get, and basically if we look at ray tracing, it kind of tells you about how we bend over noise. So downwind is going to be noisier and you'll get decreased noise. Upwind of that, something that's not really that important. It is important, however, for some of the other structures that we'll talk about, like the batteries later on, is temperature inversions. I'm not too familiar about if that's an issue here in Ireland, but it's certainly an issue here in Australia, where temperature inversions can add a good 7 to 10 decibels, given the right conditions of adiabatic inversion of the adiabatic lapse rate. And that can enhance noise quite a bit out to 2 and 5 kilometres. We have a lot of that issue with the mining industry, but we also do see it now with some of these. What concerns us is some of the battery storage systems that are associated with wind farms. Now, a lot of predictions in Australia are done using Concowie, but probably most of them are now done using ISO 9613, which I'm sure everyone's familiar with. Just flagging that, as you would all know, ISO 9613 already inherently builds in a downwind source to receiver wind vector, and has an increase in noise associated with that prediction. So it assumes that every wind turbine is upwind of a receiver, when we know that in reality that's not going to be the case. So it is a very conservative assumption, and in fact, when we do look at things, what happens is seasonally you will get winds from one direction and not from another, and these are the things that we have to think a lot about when we're trying to regulate noise. How much noise, if someone's only going to get it for a month a year, or are they going to get it for 6 to 8 months a year? Are they going to be exposed to different noise levels? Is one number that happens once a year, never to be exceeded, is that going to be an overly over impost on a resident, or should we be looking at what's averaged over a whole year? So there's some of the things that we've had to think about in our regulations. We also use the UK's IOA practice guide from 2013. So pretty much everyone uses that for your source receiver across valleys. So that's inherently an additional conservative measure that's built into most predictions. We tend to find that our predictions are generally on the conservative side. We in Australia, we haven't been finding that they've regularly been under prediction of anything. One of the things that we've got in Australia, though, we were a federation that made up of a number of states, and environmentally, most legislation is not on the Commonwealth, so it's not a federal legislation. It's a state-based legislation. So one of the things that we do find is each state tends to come up with its own numbers and regulation, and in a way that probably happens in a lot of places. Someone like New South Wales will come up with a number, and this is across the board, whether it's road, rail, industrial noise. Somewhere like New South Wales might come up with a number. Victoria will then look at that number and they'll go, okay, New South Wales is using their number. Let's go with those guys. South Australia will then look at Victoria and go, we'll do something similar. So we tend to have things that are fairly similar. The only problem is when they go to review it, then they look at, go, well, does this document need to be reviewed? And they go, no, well, the rest of Australia is doing very similar, so our document must be fine. So it doesn't work out too well to us. But mostly what happens is states generally adopt the South Australian guideline. South Australia is one of the states that has the highest number of wind turbines in it. It's got the highest number of generated power. And we've got about 110 wind farms across Australia. And that's about 13% of our needs, and that's a total rated capacity of about 14.5 gigawatts of power at any one time. South Australia at some points has reached full use of energy in its domestic use, but that's not the case for the more industrial states of Victoria and New South Wales. But the South Australian guideline forms the basis for a lot of documentation. The other one that's used in our other states is the New Zealand guideline, which is also a contemporary and good document that's been used mainly by Victoria and Western Australia usually. These are some of the guidelines here that showing you the different states in Australia and the base limits that they use. Most of them are a certain number, such as 35 to 40 or background plus 5. So that's the consistent approach that's used, that as wind turbine noise increases, then the background noise is also increasing. So it's about how much it exceeds and emerges above the background noise that's important, but they're the base limits. All except Tasmania, that actually really holds tight on 35 decibels. Consequently, they don't have very many wind farms there, and they've got a lot of hydro that meets their sustainability targets there. But today, what I'm going to be talking about is mainly New South Wales. That's where I live, and that's where I've been involved in the guidelines. We use the South Australian guidelines from 2021, but we've added to those and we've provided additional guidance in some new documents that came out in December last year, and that's what I'm going to talk about here. Before I do that, if you do come into the noise space in Australia, you will be faced with a plethora of documents. Just in New South Wales, we have got documents for road, for rail, for local government, for shooting ranges. We've got development near busy roads. We've got engine brake noise. We've got noise policy or industrial noise. It's quite a challenging space to work in New South Wales, and there's a lot of nuances on those documents. However, what we have come up with is the guideline I'm going to talk about here. But before that, you can see some of the things that we've got up here. You will notice that there are different guidelines or different targets depending on what is the noise generating apparatus there. And no real surprise, wind farms have one of the lowest noises, probably reflecting the amount of community concern about noise being generated from wind farms. Rail, they get their bonus, the 65 decibels during the day, 60 at night, a little bit higher than road, which is less less acceptable in the community. And then we've got industrial noise as well. But wind farms have got a particularly low level of tolerance in New South Wales and Australian communities. So the documents I'll talk about here is the Wind Energy Guideline, and two parts of that I'll talk about tonight is the noise supplement, but also the visual guidelines, which, to be honest, since the visual guidelines have come into play, they've actually almost made noise redundant. So they have really ruled out a lot of the turbines that would have caused in excess of 35 decibels at night, just on a visual basis. So that's something that wasn't necessarily expected. Those two documents, those two technical support documents, are part of the whole bundle that comes in under the Wind Energy Guideline. And to the right there, you can see the process of the planning of state significant development, which wind farms and energy production come under. So that's the process of an assessment that's required for these wind farms. And we're talking generally big wind farms as compared to maybe what you see in Ireland, where you do have some much smaller ones. Most of the ones we're talking about will be somewhere between 30 turbines and 150 would be most of the wind farms for the economies that they're looking for there. It's not like it's community wind farms where you have one or two. The New South Wales guidelines, quite confusing how we've got to where we are. And that's what I'm also wanting to talk a little bit about. Prior to 2010, we just adopted the South Australian guidelines from 2003. And you can see there was a few efforts to come up with our own guidelines. There was an effort made at one point to have an Australian standard across the board, but no one really ended up adopting that in any of the states. And currently we're adopting the most recent version of the South Australian guidelines, basically still a 35 decibels or background plus 5, 24-hour average, modified in New South Wales for things like tonality and low frequency noise. So going back to the visual guideline, it's kind of interesting. If anyone, I can provide the links to this, but you can kind of Google it fairly easy if you look for New South Wales guideline. They're quite an interesting read. The main thing is that we've got visual prominence of wind farms of large ones and large turbines. Some of the ones we're looking at in New South Wales have hub heights, something in the order of 160 metres, maybe a bit higher. And by the time you put on a 70 or 80 metre blade on top of that, you're getting up towards 250 metres. As you can see from the scale there, they're really they're becoming quite prominent out to quite significant distances, and dominant to a point of 1.5 kilometres. And I would expect in Ireland, where your landscape is a fairly important feature of Ireland, that this would be something that would also come into play here. I'm not sure if it is or not. I don't know if you guys have visual guidelines for these or if they've been actually documented, but this is where we're at in Australia with turbines that becoming a common feature up to 8 kilometres away. I tend to see the farms and turbines I've seen here on my travels have been much, much closer to probably what I'd expect a non-associated residence. So that's maybe something that'll be of interest going forward. But in terms of noise, the South Australian guideline, there's 2,000 data points with a minimum of 500 downwind. That was in the old guideline. It continues on. The New South Wales modification to that was that we limit that to 6 weeks of data collection. Often some of the directions that were downwind were often very, very challenging to collect a lot of clean data points there. The receivers that we've got are often at large distances, and trying to measure a wind turbine at 1.5 or 2 kilometres can be quite difficult. So one of the other things that the New South Wales Guideline does, it allows you to make your measurements in intermediate locations. Now, the special auditable characteristics that we look at, we refer to the ISO standard 1996, and it's in third octave. And we look at also low frequency noise is assumed that pretty much if you look at the spectral information from a wind turbine, if you had a dBc of about 60 decibels, you're not really going to have any low frequency noise. We have a penalty scheme for that. If you were, then it invokes a 5 decibel penalty. Mostly we find that that's not a problem. We've moved to, rather than using a regression line and a third order polynomial, we actually are now binning the data that we get into single integers of wind, and that's given us a bit better of a way of assessing the noise impact over those different wind speeds as they increase as the noise increases with the wind speed. As you can see there, the main thing is that we look at is for non-associated receivers, it's 35 decibels. So considerably less than you have in Ireland and England. Associated receivers, they're ones that are associated to the wind farm. They have some kind of arrangement with the developer, and that can be a financial or otherwise. They can have levels of up to 45. But the main one that's the issue for a wind farm developer is meeting that 35 decibels. Now, what we find with background noise, and I'm sure this is the same for everybody, it's very difficult to be measuring it, especially at the distances we're doing. We require the meteorological mast to be at hub height or close to that. And what we found that filtering out a lot of the noise gives us kind of a pattern that you're seeing there. And it is possible to make those measurements in 10-minute intervals. That's the process for measuring the background noise. After a wind farm is built, there is a compliance period where they must go out and do the measurements. And these are the things that we're looking at here. The downwind analysis is needed to be done. So you're looking at those worst case scenarios. And they're the kind of background trend levels that you will get at a typical wind farm. Filtering it, there's a number of ways that are documented on how you can filter your noise to get a better true representation of that. And then you'll derive the wind farm noise as that which is minus your extraneous noise. So consultants will have to collect a lot of data, and they'll get a pattern that looks somewhere like this. We're only really interested in that up to about 12 meters per second. After that, we know that the power band will level out, so that won't be an issue any further than that, and it'll only be extraneous wind noise. The modification that we've done, South Australian Guideline, they have to measure it at the receiver. We found that was too difficult in New South Wales. The technical supplement allows measurements to be made at around about 500 metres, where you get a better signal to noise ratio. At about 500 metres, you might be able to be measuring things at about 50 decibels, 55 decibels, which is a lot easier to differentiate from the extraneous aeolian noise. Measuring at 1500 metres is, I would say, diabolically difficult. It's really, really difficult to assign a noise level and a number to a wind turbine. When you're looking at generation of levels that might only be 37 or 38 decibels, very, very difficult to assign that to a wind turbine when it's only maybe a decibel or so above the background noise. Hence, we find that this intermediate approach provides much more assurance, particularly if you start to look at audible characteristics such as tonality. So on this graph here, what we're showing is how this allows us to get a better signal to noise ratio. I'm not sure. I think your measurements need to be at the receiver here. Probably if your properties are much closer than 1,500 metres, that makes sense. But we have properties that are on the borderline of meeting 35 decibels, sometimes out to almost 2 kilometres. So very difficult to measure a clean signal at 2 kilometres from a source in a windy environment. The New South Wales Technical Supplement, cumulative noise, we don't have a cumulative noise, but given that we're starting to get multiple wind farms built next to each other and they're quite big, it's probably prudent for us to start looking at that. And that is one of the things that will probably come forward in any other future assessments. National parks, for the first time, we've introduced a number. Not a lot of background on that number. So what has been applied is what has been considered for national parks as an acceptable level for humans. So we're looking at an average level of around about 55 in there. Our national parks, they tend to be the areas where we've got lots of trees, so it's very difficult to measure in a national park. The national parks are often quite big, so really that level is at the nearest accessible point, which might be, it might be up a kilometre or so inside a national park boundary, because our national parks are quite big. Usually it's not going to be a big problem, but this is the first time a document has started to look at putting a level in consideration. What's happened of recently compared to several years ago is we're starting to get these ancillary assessments that now need to be done. And the noise policy for industry actually applies to stationary noise sources. So that's a different document that applies to your substation and any other things like a battery energy storage system. And these can be a little bit of a constraint. Sometimes they happen to be located a lot further away, potentially near other non-associated receivers. And the noise levels associated with them, we're actually starting to see they can be slightly problematic. One of the things that Dermot flagged to me, actually, I hadn't seen this while I've been here in Ireland. I did notice that the High Court has ordered some turbines to be shut down during certain periods of time. Very interesting case. Very interesting to see how this would go. Some of the comments that the judge made is really questioning the robustness of your documentation. This has happened in Australia as well. It hasn't happened in New South Wales. Our guidelines tend to be about 5 decibels more stringent than they are in South Australia or Victoria. But in both of those two states, they've had significant challenges to larger wind farms. I can see that this might be going this certain way. The judge has ordered that those turbines be put into a containment mode or a low noise mode during certain periods of time. And it would seem that she has said there wind speeds of 5 to 11 metres per second, which is really, it basically covers the whole gamut of when the wind turbine would be operating. And certainly it's the most productive wind speeds for that. So I couldn't see that turbine being economically viable if it operates and it has to be shut down under some of those speeds, if it's the wind directions are such that it's causing this amplitude modulation of that. I know that the IOA has had issued a lot of guidance on amplitude modulation. We in Australia tend not to look at it because it just seems to be one of those things that we can't assess it properly. And if we can't do that, we try not to try and regulate it because to be honest, I think it's diabolically difficult to do. And if you can't do it, then you probably should question whether it's another way of doing things. We've reduced our noise targets, as I said, down to 35 decibels, where the UK and Ireland will have 45, I believe, during the day, 3 at night, much higher. We assume a certain level of amplitude modulation will always be there, and we account for that rather than trying to allow for an excessive amount and then trying to measure it. It's difficult. We used to we tried for a while looking at a range in peak to peak of 4 decibel difference and saying that was acceptable, but we actually moved away from that because it was really hard to measure. Very interesting to see what will happen going forward. And if anybody would like to keep me posted on that, I would be interested in seeing how this goes and comparing it to some of the court cases that have happened in Australia. Right now, I don't know if there's any questions online before I start to talk about other renewables, if anyone wants to give any questions or if there's anything, or if we've got time to actually move on to some other things.
We've plenty of time. I see one question in the chat. That's welcome. No questions. Do you want to keep going, Jeff, and we'll save the questions till the end then?
Yeah, sure.
Yeah.
Okay. So some of the other things I thought I'd talk to you tonight about were the challenges that we're facing with other renewables in Australia, and the associated noise that comes with those. As I said, I was going to talk about solar farms, probably not that relevant to you guys, unfortunately. We'll see what climate change brings into the future. But it's a big thing in Australia. They are a big thing. Are they noisy? Well, you would intuitively you would say no, they're not. But that's not completely true. There's a solar farm that I'll use as an example here. That's proposal. It hasn't been built. This one, we have several that have been built. But this is a fairly big one. It's 80 megawatts. So I looked at what was being proposed. It's going to have it's going to have 17 power stations comprising 102 inverters. Now they've got a sound power level in the order of about 95 decibels. The thing that can be a little bit annoying is all of these panels, they've got motors that then track them, so they follow the sun. And there's a hell of a lot of those. So although we mightn't talk about individually large sound power levels of individual units, we have a lot of units, over 6,000 of those. Now, there's only one transformer. It's noisy, but you look at the noise from the tracked panels, and if they all start to move, now they only move for about 1 minute in every 15, but 6,000 things at 78 decibels, you do the numbers, they actually start to be quite audible at distances. Obviously not an issue at night, so it's only a daytime thing. So we don't really have too much problems about them, but just something to be aware of. Battery storage systems, BESS, has probably been one of the things that we actually are having some issues because they tend to be located close to substations and often in areas where there's more residential dwellings, closer proximity of residences. BESS is also starting to become a big player in supporting data centers, which are highly energy intensive users. They are always located in highly urbanized and suburbanized environments. So the generation of noise from these things is not particularly unique. The industrial noise policy, one of those documents that I flicked up before, covers the noise generation of these pretty well. But this is new technology, and it's like when wind farms first came in, we didn't really know how to assess them properly. There wasn't good information on them. We didn't know how they'd be set up. Manufacturer data was not good. It was different from one kind of piece of equipment or manufacturer. It varied quite a lot to another. So the main things that you've got that generate noise are inverters, batteries, transformers, and then the high voltage transmission that you get from those. And the challenges are the lack of detail on that, and it's really quite variable. The inverters, data's the problem. We don't have much of it. We don't see much of it. Not a lot of these things have been installed, so we actually don't have that empirical data collected by consultants. They're measured to the normal ISO standards, 3744 and 9614. Consultants tend to take a fairly conservative position, and that's admirable, but it can be a bit of a problem. Tonality, we do see that coming through in inverters, mainly around 100 hertz, which is a function of your 50 hertz signal and the sine wave. So you get a 2 times that, you've got a 100 hertz frequency problem. And we are trying to collect data on that into the future. The batteries themselves, the fan cooling systems on these things is quite variable. We have operating temperatures in Australia that they will operate from probably the low 20s to maybe on the hottest day, you might be in the 40s. One of the things that we're struggling with is if we set objectives for these battery systems, and if Tesla make it, so they've got this all-encompassing one battery system that they'll bring in, and it's all contained. Whereas some of the others are more bespoke and they're modular, bits and pieces will be designed separately. They can actually be quieter than a Tesla, but a Tesla is a very known source of those things. And they tend to operate, obviously they're able to operate under high temperatures, but fans of those and the cooling that's needed changes a lot throughout, whether it's charging or discharging. And the things that we've got issues with, do we make them and assess them against 100% of what they could potentially do? Because the fan systems tend to have a lot of redundancy built into them. So for us to assess them at 100% of their potential capacity is probably very, very conservative, given that they don't tend to do that. They tend to operate on a much lower level of maybe 50 to 60% of their ability. So that's a struggle on how we should do it. Should we look at a worst case, or should we look at some kind of realistic likely case of those? The transformers are similar. We don't have that much information on them. We try to get that from suppliers. It's not that particularly easy to do that. They do come out with the tonality that I spoke about. But the noise control of transformers generally tends to be a lot easier than it is with other parts of the BESS equipment. So I'm not sure if there's a lot of battery storage in Ireland, but it's probably going to come, and it'll probably be around data centers a lot, which tend to be in more urbanized areas because they're highly intensive use of that. So it's probably something that the consultants will need to look at in the future, and it's probably something that would help if we all had some response on those. Again, the big issue is we don't have good data on them. The data we do have shows that there's some variability especially down in the lower frequencies, which are going to be problematic because they're the frequencies that don't get attenuated if you're in buildings and you're inside. These low frequencies down here, 200 to 500 hertz, is probably big issues. Not a big problem if something's up at 2 kilohertz, not going to really come through your windows. You've got fairly substantial buildings because of your temperatures over here. Your glazing is good. We don't have that level of building necessarily always in Australia. We have quite long frame buildings, but still anything much over 1,000 hertz, it's not going to really be a problem internally. It's those low frequencies, 300 hertz, probably in particular. So again, coming back to what I was talking about, is it conservative for us to measure that equipment and its optimum output, or should we be looking at something a bit different? And we have been looking at that. The sensors will operate, they will range from 10% to 100% of their potential output, and that's about a 10 decibel differential there. So, that's something that's going to be really, really hard to work out legislatively and in an assessment way. If one of these is going to be located in an environment, is it going to be running at somewhere, well, will run somewhere between 10 and 100%, but what's going to be the level that we should be setting for that to manage those community expectations of noise that you will get from these things. One of the other things that happens though, is it's not only the charging of these things. What we are starting to see, or we expect to see in Australia, is that the market will drive the use of things like battery storage for them to buy energy, not necessarily produced by other resources or renewables, but they'll buy it at maybe 4 o'clock, 5 o'clock in the morning. They might sell it 2 hours later and make a 5 times increase on their cost. They sometimes maybe buy it for 6 cents a kilowatt hour. They might be able to sell it for 30 cents 2 hours later. So a lot of money can be made by its operators and owners by the short-term buying and selling of that energy. So although you might think that they're not going to be used that much at night, that's probably not necessarily always going to be the case. If they're close to a source of energy that they can buy during the off-peak times and then resell a couple of hours later, that's a big incentive for them to actually do that. And again, we don't know that, but the use of data centers, very intensive energy users, will be one of the things that drives this. So they also need to have a lot of redundancy built into their centres. So these tend to be located close proximity. It also shifts the frequency bands and the usage of those, whether they're operating at a low level or if it's much higher, frequency tends to rise a lot. The expectations at the planning stage, about how much confidence we have in how much noise is going to come out of VESAs. We're quite concerned in New South Wales that we will get this right, because they are being proposed to be put in highly urbanised areas, and the simplified models can work, but we don't have a lot of confidence that they're actually going to be as accurate or necessarily predict the amount of community annoyance that we'll get from some of these infrastructure that we're putting in. So the EIS, the environmental impact statement documents that we have, we need those evidence that these VESAs will work and that they will perform as predicted. But getting designs that are constantly changing an impact statement might come 3, 4 years before development. The technology often changes over that time. And that's one of the things that we're also a bit concerned about, that what gets approved is then not necessarily what's going to be built in the end, and there'll be modifications and noise levels will go up. They'll be proposed to go up, and then we are struck with trying to manage how the community perceives that kind of noise, and often there's quite an amount of community concern about that, and rightly so. The challenges that we've got, I think we've gone through them. They are extensive. It's hard to anticipate what they might be. As an acoustic consultant out there, you're really in a brave new world. There's a lot of lack of information. There's evidence control that will often be suggested that may or may not work for these things. There's a lot of proposals that we get for restricting the use of containment modes with fans and so forth that make things a little bit difficult. So to really know if it's possible and if it's reasonable and feasible for it to be implemented. So that's some of the things the engineering controls to ensure that a compliant outcome will happen. It's a point in time where we're actually not quite sure whether some of these things will work as being proposed, or whether it'll end up being minor exceedances that end up being quite difficult to manage. Some barriers that get proposed aroand vessels that I've seen recently, they're talking about like 8-metre barriers that go around these things. I mean, from a visual point of view, in an urbanised area or even in a rural environment, they're probably going to be unacceptable at those levels, those heights. So enclosing them increases heat, which becomes difficult. So there's not too much you can do with some of those. So it's going to be interesting times ahead. In summary, it's about good quality data that minimises the risks that to the project. Tonality tends to be something that's overlooked. We do see that with anything electrical. 100 hertz and harmonics of that can be problematic, especially from some transformers. We need to recognise that there's a lot of time for development, and it's very important for those of you that might be out there tonight that engaging with an acoustic consultant is probably very important, and seeing what stages you can be involved in, because the designs will often need to change, and that's what we're seeing is the directionality of noise and the locations of these will need to be tweaked a lot, and that's one of the things that we're seeing that's been problematic for some of the renewable energy sources that we're getting. One thing that, a little bit of an aside, one of the things that we're also seeing in Australia, and a lot of questions but not very many answers, relates to corona noise and aeolian noise of overhead transmission lines. What has happened in Australia is most of our energy was generated by coal. Australia's got abundant coal resources. We export a lot of coal. It's a big generator for us in terms of gross domestic product. The coal tends to be located towards and fortuitously highly populated areas, particularly. And over time, the power stations that have grown up around those have had their transmission lines, and all of the interconnectors have tended to take that energy and disperse that out over the state. What's happening with renewable energy? Completely the opposite. Renewable energy, because it takes up a large footprint, and needs to be located in areas that are cheaper or closer to wind resources, which tend to be inland. Tends to be located more to the west of the state or the northwest of the state, and then try and feed the electricity back to the main cities of Sydney, Newcastle, Wollongong. And we're going through this period where we need about 10,000 kilometres of new transmission lines. Very, very expensive putting these interconnectors in there. We're talking 500 kV lines all over New South Wales. And this has been problematic in a whole bunch of areas. But one of the things we get questioned a lot on is corona noise and aeolian noise. And we don't have guidelines for these. And there's not even that much information out there. So to basically talk about a little bit here, I won't go into too much about it. There's a lot of key components. There's the tower itself, there's the conductors, there's the isolators, and there's a lot of the ground wires to protect from lightning and so forth. But the diagram on the right-hand side gives you a generic impression of what those towers are. They range in height, often depending on what kind of voltage they're carrying and the distances that they have to keep the wires apart. As I said, some of the ones that we're now looking at in New South Wales that are carrying a lot of current need to be these 500 kilovolt ones, and you've got heights of about 60 metres with those. Corona noise, if you didn't know what it is, it's the ionisation that occurs. It's a crackling sound, and it's the implosion of those water droplets that might be in the air. Happens with humidity, doesn't necessarily have to be raining, but often happens around when there is rain or just afterwards. And it's most likely a problem then, but it also can occur with dust or very minor discontinuities on the wires themselves. And the risk of corona noise includes the voltage, obviously. Generally, it's considered that it's around about 300 kV or 250 kV and upwards is problematic. But what I'll talk to you about here is some issues that we're seeing that much lower voltages to that. So it's got to do with the surface gradient, the sizing of the conductors, the age of the line also can play a role. Strangely enough, it seems to be newer lines that are more problematic, and we get less issues as the lines get older because they tend not to have oils and manufacturing grease in the lines that also causes corona noise. So the current best practice is actually that we refer to in Australia as a document that came from Ireland and from EirGrid. And that document also consistent with general practice says that it's only really an issue over 350 kV. And that document recommends separation distances of about 100 metres from a line or 200 metres from a tower has been a good default position, and that's what we try to use in Australia. Difficult sometimes when you're doing 10,000 kilometres of new line. Prior to that, predictions have just been used using, it's like the EMF calculations, and it's the bottom bill power administration method, which is, basically it's just an Excel spreadsheet that looks at the propagation of distance and includes a couple of effects, and includes humidity, but not really rainy conditions. The case study I'll talk to you about here was 500 kV transmission line in Victoria. It was a very old one. There was no real complaints about it. One of the consultants that's provided me some data, they did some measurements around there and they filtered the data, and on the graph on the right-hand side, you can see what that looks like. Higher relative humidities, no real rainfall. And The LEQ at the tower ran about less than 40 decibels at the midpoint. Highest levels of about 45. Audible, but not a dominant tonal character. Gave a sound power level of about 78 decibels. That's for 500 kV. Problem was they then had a newly installed one, which was only 132 kV, and connected up to some of the similar substations in the area to disperse it. And it had a similar sound power level, but it was much closer to resonances. So you had these levels that we shouldn't have been near as high as they were measured to be. And it was a problem because these lines were quite close to a number of houses. So what the investigation did, because I mean, they basically couldn't energize these things properly, it was found that a lot of the insulators had a small amount of dirt on them. And it wasn't something that could be just washed off. They were actually in areas that were quite difficult to get to. And it wasn't, they're supposed to be a bit self-cleaning, but this wasn't happening. And they got a noise camera specifically to look at corona noise. It's looked at it. It was identified. It was this insulator noise, and it was quite noisy at the properties, and it was also tonal. Very big retrofit to come along and then go up these towers and replace lines. Very difficult thing to do. And mainly it was only because they had been installed and they weren't particularly clean. They'd been lying around, I think, for several months before they were actually installed and the towers were put up. So that fixed some of the problems there. So some of the things that we're looking at with corona noise, the design principles are, the route selection, trying to keep them away and following that EGRID guidance document, keep them away from sensitive locations, sensitive users, residences and so forth. The design of the line to minimise the surface gradients, voltage gradients, to use insulators with large radii and avoid anything with sharp edges on it, which tends to increase the issue that you have. And in some cases use corona rings where appropriate. And they don't tend to get a lot of maintenance, but really, at least when they're going up, they need to have the insulators as clean as they can be to make sure that you're not going to get any of those ionisation of dust and dirt particles. Aeolian noise, that's just the wind going over these lines. A bit of an issue again in Australia. We refer to that EGRID study that provided some guidance on that, basically saying it's not as common, but you shouldn't really have a problem with it. There's been some information that's available on that. It's all wind tunnel assessments that were done. And the design of the wires has a lot to do with this. I won't go into too much detail. You can look at one of those references if you do. It's about the cross-sectional area and how it's actually designed so that the wind doesn't tend to cause basically a trailing edge noise coming off them. Again, all wind tunnel test results, we don't really see any empirical data for aeolian noise off transmission lines. If anyone does that, I think we'd all be interested in that. Would be some good conference papers, I think. It's the spiral rods that tend to be issue, but it's not to be that big a deal. Obviously, if it's related to if you're getting a wind that tends to be enough that it's actually causing some of this noise, but it's not enough to cause a lot of foliage noise that might mask it. Tends to be one of the case studies that they did look at that case study 2, there was aeolian noise. It was around about 500 hertz. And it was around 75 decibel sound power level. So not insignificant. And they tried to do some things. They changed the towers and the way they held held the wires. Didn't really happen, but tends to be something that we just don't know about, but might be a bit more of an issue for us in Australia as we have to put in these new interconnectors to bring the power from out west towards the cities. So what's the summary of that? Well, again, route selection, use of spiral rods. Those protrusions seem to enhance turbulence. Use of composite insulators instead of glass or porcelain seems to be a way that also reduces it, and use of different profiles. Summary of that is that these new transmission lines, they're bringing risks of corona noise and AOLU noise to us. As they cross residential areas, we're going to have more issues with them. But most of the mitigation, to date, it's primarily involves line design factors, and it's mitigation after the fact is going to be very, very difficult to move anything or to change things once these lines have been developed and the routes have been decided is going to be very difficult. You would have already done all these other studies, particularly relating to biodiversity offsets and anything related to that as well. So moving a line, not a very easy thing to do. So that's probably, I've whisked through that because it was basically about 65 or 70 slides. A lot of the information I've got there was provided to me by Marshall Day Acoustics, a large acoustic consultancy operating in Australia, and also Resonate Acoustics, who did a lot of the work on the on BESS and on the corona noise. I'd like to thank those, and happy to take any questions.
Jeff, I think we have to leave it there, but thank you so much.
No, thank you for everybody coming, and if I've been, if I can give one last little punt, if anybody of you make it to Internoise, Australia is hosting Internoise. If you are interested in wind turbines, it's held in Adelaide. There will be a lot of sessions on it there. That's the state that has most of the turbines, and we can certainly have lots of things to talk about, and maybe even visits some of the wind farms if you come down there. Put that in your diary. For those of you here, I've left a few save the date cards, and we might see you guys there. So thank you all for listening. Really appreciate that. I hope that says the right thing in Gaelic.
Yeah.
Because I trusted an Irishman who I was not quite sure he was going to tell me the right thing. So make it. Other than that, thank you very much for your time. Appreciate you having